Good morning, everyone. Welcome to the new seminar season of IvS 23-24. It's the very first seminar, yeah. I agreed to open the season, and I guess we are very happy about that. Hearing about massive stars today. Emma, she received her bachelor and master's in France, I believe, in Paris, right? Then she's been to ISO, to Chile for a couple of years, yeah? And now she's standing in front of you, presenting forming companions around massive stars, the high angular resolution view. So I believe we will learn a lot about interferometry today. So Emma, the floor is yours now.
Good, thank you. Do you hear me well? Perfect. Yeah, good morning, everyone. I think I know most of you, but there are some faces that are not familiar to me. So I'm Emma, a PhD student in the team of UG. So I started my PhD in 2019. And then indeed I went for 2 years at ISO in Chile. That was during the pandemic, so not that easy, but now I'm back here in Belgium. And I'm really happy to be here with you today, standing on my 2 legs, or should I say 1.8 leg, to present the first seminar of the academic year. So yeah, I'll talk about the formation of companions around massive stars, and I will put the focus on the high angular resolution techniques. I am an observer, so I think it's nice to start this talk with a beautiful image of the different multiple systems that were found in the Orion star-forming region. Just to remind you that multiplicity is a common feature for stars, and if we look more closely at the numbers, it's also clear that multiplicity is a common feature for most stars. And there is even a tendency towards 100% of multiple system for the most massive stars if you look at the upper right hand of this graph. Multiplicity also appears early in the evolution of stars, so this graph focuses only on young stars, whatever their mass is. So we have the multiplicity fraction for low mass stars, but also for high mass stars. And what I would like you to remind from this plot is that we measure multiplicity and binarity even in the youngest stages of stars. So in order to understand when and how the multiplicity is set, we must look backwards to the star formation process. So I will give you some hints about low mass star formation. It's really simple because this is not something I would like you to remind from this talk, but just to set a bit the context. So for low mass star formation, if we only focus on single stars, so stars are formed from a cold giant molecular cloud, where eventually, thanks to a source of energy nearby, such as the explosion of a supernova, for example, the areas of overdensities and the different clumps will start collapsing and it will form a dense core. In order to preserve the angular momentum, all the material that is infalling will also flatten into a circumstellar disk. And then you will have a central hot core, but the material around the hot core will still be accreted onto the central star through gravity. So yeah, this core will keep accumulating, and you will have also bipolar outflows that will break out, and they will be confined by the disk to flow out along the 2 poles of the stars, and the rising core will gain in temperature, in mass as well, and eventually will sweep away the cloud material and stop the accumulation of additional mass onto the star. But you will have this remaining accretion disk around the star, and also some jets. So this is what we know for low mass stars. Eventually, you will just have this accretion disk that can become a protostellar disk, for example, and you will be left with a solar system. And low mass star formation is pretty well known, also from the observation side, because they are pretty bright in different wavelengths. So we can actually have snapshots of the different stages that I just talked about. Using ALMA, for example, GWST more recently, Sphere at the VLTI, but also, yes, apex in the radio, like you have really nice understanding of how low mass star formation works from a different range of wavelengths. For high mass star formation is a bit more difficult because at this stage of the protostar that we call the massive young stellar object stage, the star and the accretion disk and all that is really bloated in a dusty envelope and is really opaque to the visible wavelengths. So it's really hard to observe them, and why we have a missing block in our knowledge is mainly because they are really massive and really distant, around 2 kiloparsecs away, and their lifetime is really short. That also reflects in the formation timescale. It's around 10 times shorter than for low mass star formation, so it's really hard to spot the different stages in the massive star formation. They are very embedded and optically invisible. And also, most massive stars are found in multiple systems, so we should rather see massive star formation as multiple formation rather than just single massive star formation. Now, how we can form companions around massive stars or around all the stars. So there are two main processes, I would say. So first, it can form at different scales through fragmentation, and the fragmentation can occur at different stages during star formation. So it can occur at the very early stages during the collapse of the giant molecular cloud through the filament fragmentation. It can occur a bit later on when the giant core will differentiate into two different protostellar cores. So you will have a core fragmentation here, and also the disk fragmentation that occurs later on once you have the accretion disk that is set around the forming star. There is another category of another channel to form companions, if I can say, and we call them the dynamical evolution or dynamical interactions. That can be the capture, for example, two initially unbound stars can eventually, through, I don't know, close encounters, remain as a bound system. Then there is also the migration through interaction with the disk. So once you are formed companions in the disk, this companion can migrate, and it can also change the binary statistics and parameters. And also quasi lead-off cycles can happen in the case of triples, usually highly eccentric systems, and this also is really prone to affect the binary statistics. Good, so I adapted this sketch from the paper of Hugues Sana 2016, just to show you how we can probe the different multiple formation channels based on the different observing techniques. So the spectroscopy has been used in 2012 to show actually that 100% of massive stars, nearly 100% of massive stars are found in multiple systems, and that there is a tendency towards short period binaries, because with spectroscopy, of course, you are probing very short or tight systems, if I can say. The first project I'm going to talk about talks about long baseline interferometry, where we try to look at wider companions, but still close enough. And the idea is to understand whether or not disk fragmentation and migration can occur. So the idea is that if we can spot or detect companions between 1 and 100 milliarcseconds, it means that disk fragmentation or migration can have produced disk companions. Okay, so yeah, the multiplicity, I will talk about the multiplicity of young O stars with optical interferometry. So we are trying to see whether there are single, binaries, triples, or even higher order multiple systems. Okay, so to observe young massive stars, first we have to choose a suitable population of young massive stars as a pilot study, first to see if the techniques that we are using are the good ones to probe this multiplicity in young systems. So we looked at this graph from Claudia Ramirez-Tanus, and she worked, I think, closely with Hugues Sana around 2017, and they found that M17 is a cluster in which the radial velocity dispersion is really low. So she plotted, she looked at the radial velocity dispersion in different clusters, and she plotted their radial velocity dispersion as a function of their age. And as you can see, M17 shows rather low radial velocity dispersion, meaning that there is a lack of short period binaries, and that the binaries are rather found at wide separations. So we think that M17 is a good laboratory to test this migration scenario. And why? Because it's one of the closest star-forming region, 1.7 kiloparsec. I know that for some of you it might be quite far away, but for the massive star community it's rather close. It's one of the most luminous and youngest star-forming region in our galaxy. And yeah, it's the perfect laboratory to test the migration scenario. So we have a sample of 6 younger stars in the central cluster where there are most of the massive stars. They are the rather bright in the K band, sorry, and they are of luminosity class 5, so we know that they have already reached the zero-age main sequence. So they are not really at the formation stage, but they have just left the formation process, and they have reached the ZAMs. And in literature, we can find already 5 spectroscopic companions for these stars. So now that we have the object, we have to define the wavelength and the technique and the instruments that we want to use for the observations. So as I said earlier, young massive stars are deeply embedded. They usually peak around 100 microns. So if you want to maximize your chances to detect an object, you should go to infrared wavelengths. In optics, it's really, really opaque. Oops, sorry. And then, so to detect the closed binaries, we want to try to detect companions between 1 and 100 milliarcseconds. Then we need high angular resolution. So we decided to go with gravity because, as you know, interferometers are a good way to overcome the diffraction limit of individual telescopes. So yeah, we use the near-infrared and K-band interferometry with gravity. On top of that, we use the UTs, so the unit telescopes, instead of the small mushrooms that you see, because we are still really at the edge of the capabilities of gravity. So we need the big mirrors to collect as much photons as we can. So yeah, we had this proposal with gravity and the UTs. Good, so we have both of that. We made the proposals, we got the time, they were observed. I spent a lot of time reducing the data, but I'm not going to talk about that. And directly jump to the interferometric observables. So I'm not sure if you're all really familiar with interferometry, so I think I will just give a quick overview and introduction of the observables and what we can get from them. Cool, so as I said, interferometry can overcome the diffraction limit of the individual telescopes. So then your angular resolution becomes lambda over b and is no longer lambda over d, which is the diameter of the telescope, but rather a distance of the between two telescopes, what we call the baseline. The most common measurement in optical and infrared interferometry is the measurement of the amplitude of the fringes. And the fringe contrast is often called the visibility of the fringes, which is what you see here, what we call in the community the squared visibility, the V2. So an unresolved point source will have high contrast fringes and a normalized visibility at 1, as you can see here. That means that the size of the object is much smaller than the angular resolution, so you are not seeing anything, just like a point. For a spatially resolved star, though, is a bit different because the light from across the stellar surface combines incoherently, and this will cause a decrease in the fringe contrast and therefore a drop in the visibility amplitude, as you can see here. So the normalized visibility for a resolved source is usually less than 1. And from that, people used to, for example, measure the size of stars. I know, for example, that Miguel Montarges, former postdoc at IvS, used to do that for Betelgeuse to measure the difference also in time in the diameter of Betelgeuse and all that. Okay, so for a binary star, it's a bit different because a binary star will produce 2 fringe packets and 1 for each star in the system. And if the separation between the stars is small enough, the fringe packets from each star will overlap and it will produce this periodic signal in the visibility. The separation between 2 peaks in the visibility provides you a measurement of the binary separation. So keep in mind that this visibility is a Fourier transform of what you see in the sky. So if you have a big distance between these 2 peaks, it means that the binary system is rather tight. Conversely, if you have short, like a lot of wobbles in your visibility patterns, it means that your binary system is rather wide. Okay? And then the minimum visibility reflects the flux ratio between the 2 components of the binary. So just with this just with this visibility pattern, you can get a lot of information about the multiple system. And then there is a second thing that we call the closure phase, which is to retrieve the phase information. So unlike radio interferometry, in optical and infrared interferometry, you lose the phase information because of the turbulence in the Earth's atmosphere that corrupts the phase of the fringes at optical wavelengths. So to recover the phase information, we combine the phases measured in the closed triangle of telescopes, as you can see there, in such a way that it will cancel out the atmospheric turbulence. And that way you can retrieve the phase information. So the phase is sensitive to the asymmetries in the source distribution. So if you have a central symmetric source, your data points in the closure phase will rather be around 0 or plus or minus 180. But if you have some asymmetries in the system, then you will have a spread of data points between minus 180 and plus 180. So with the closure phase, it's really sensitive. For example, if you're looking at the binary system, one is much brighter than the other, then you will have a pattern in the closure phase. For example, if you have also a binary that is surrounded by a circumbinary disk with a luminosity gradient, this will also be shown in the closure phase. Any asymmetries can be measured from this. So in practice, this is what it looks like. It's a bit, I don't know, less nice than the theory, but this is what we get. So you have the closure phase and the visibility, and you see the black dots and lines that are actually the models that I fit. So it brings me to the next point, which is how we fit the observables with appropriate models. So to do so, I used Pémoirhead, which is a tool that was developed by Antoine Méran at ESO, and he's the former VLTI expert and project manager and all that. So interferometry has no secrets for him. And I was one of the first to use actually his tool and to test it as well. So it's quite easy-ish to build models with this package. But I keep it simple because I just want to see whether or not there are multiple systems. So my models are rather simple, usually 2 points or 3 points, or I will show you later. And we check the multiplicity of the system. So we fixed the position of the central star at 0. We also fixed the flux of this star at 1. So then we get the position of the companion and the flux ratio relative to the central star. And this is an iterative process. So first I start with a single star. Then I check the chi-square. I know that I can improve it because there is remaining signal in the residuals. So then I had complexity steps after steps. So then I go for a binary, then for a triple. And if there is still some signal, then you can start maybe a quadruple. You can also try a fully resolved component. You can also try to add some disks. It can be very complicated if you really want to find what is the exact structure of the system. Okay, so the fitting results. We found 3 triples and 3 binaries in our data, with all the detected companions ranging from 1.2 to 120 AU. And the flux ratios, they range from 0.03 to 0.8. So we have one system for which the binary companion is almost as bright as the central star. Cool, and this brings me to the second to the last point of this project, which is the multiplicity results. So as I said just earlier, all of the sources are involved in a multiple system. So we can compute the multiplicity fraction, which is the number of multiples, can be binaries, triples, or even more, out of the total number of sources that we observed. So of course we find 100% because all of them are multiple. And the companion fraction, it's a bit different because we actually count the number of companion and we divide by the number of systems that we see. This results was quite like promising because, so we put here, you can see my mouse, great. The red data point, is the data point, of this work. And all the other data points are studies that were made only for main sequence stars. So we see here that if we look at a younger age, we still find this very high tendency towards 100% multiples for massive stars, even at younger ages. And same for the companion fraction. So for the companion fraction, I also added the spectroscopic companions that were found in the literature. So otherwise, just sticking with interferometry, we would find 1.5 companion on average. But if we had the 5 others from spectroscopy, then it of course increases the companion fraction. Something else that is very important is the separation. So because it can tell us about the formation path of the companions. So the data points of M17s are the red ones. So we plot the magnitude difference as a function of the separation, and we also added some other points from other star-forming regions, or also from the SMASH survey of UXNF. And so with that, we can connect our findings with the formation of the companions. So with separations ranging from 1.2 to 120 AU, the most likely mechanism to form companions is within the disk fragmentation phase. And we know that disk fragmentation is also a good framework to set up the migration. Disks around massive stars can be very massive, but also they can extend to 4,000, 5,000 AU. I think this is the only 5,000 AU is the farthest evidence that we have from observations. So to find companions as closed, it's probably that migration has probably occurred already. Also, the presence of a third companion, for example, in the triple systems, is also something that can help pushing the second companion towards the central star and leave it as a tight system as it is observed for main sequence massive stars. And this has also been tested in simulations. I refer here to the one of André Oliva in 2020, where they look at the evolution of a sync particle, and they've seen that this companion that was formed in the disk, in the accretion disk, actually started a migration towards the central star, because of course the computation time was too heavy, so they couldn't really see if it really reaches the spectroscopic regime, but it looks like it's on its way to the spectroscopic regime. And finally, capture can also not fully be ruled out, but M17 is a low stellar density environment, and also the timescales at which we think capture can occur are much greater than the actual age of M17. So it can be like an ongoing process, but it's for sure not the final setup of this. Cool, so some takeaways for this first part. So we found 100% multiple systems at the zero-age main sequence with 2.3 companions on average. Despite the cluster age and the environment, M17 shows consistency with the other studies in terms of multiplicity, but also companion fraction. And the detection of companions from 1.2 to 120 AU is really consistent with disk fragmentation theories. And I would like to highlight the zero-age main sequence, because these stars are most likely already left the formation process. So we would like to see whether the youngest massive stars also show this high rate of multiplicity. And it brings me to the second project, which is the wide environment of MYSO. So really, at that time, we look at a massive young stellar object, and we use adaptive optic assisted imaging to trace wide separation companions. And the idea is to know whether we can spot them. Do they exist? Can they be detectable also? And for that, yes, we use adaptive optics, and we use VLTI in NACO. So that was my project when I was at ISO in Chile. And we observed 13 MYSOs that were taken from the RMS catalog, which is a catalog that was built by the Leeds team in the UK, and it basically states all the MYSOs or MYSOs candidates in the Milky Way. There are just a few of them. We just know a few hundreds of them. And we use L prime band, 3.8 micron, for the same reasons I told you earlier that we have to go for infrared wavelengths. And we have a rather big field of view, which is 28 by 28 arcsecond, meaning that we can probe up to 50,000 AU, because some of these stars are 4 kiloparsecs away. Now I will quickly explain you how we go from this raw image to actually the characterization of companions. So it's the same process for all the 13 images and sources. So I did the reduction. And then for each of the images, before we start running the detection of the sources, we perform first a detection limit to get what is the sensitivity of each images and how deep we can probe for companions. Then I wrote and adapted a code from the DIO-Find and the DIO-Fault algorithm for those of you that are familiar with this code. But the main steps are doing source detection, PSF fitting, and also once we have the PSF fitting, we can derive the companion parameters. And the last step that is very important is once we have detected all these sources, we need to know whether or not they are bound to the central source, because we get this snapshot from the sky and we are not 100% sure that all these detected companions actually belong to the system. So in an ideal case, what we should do is to take the same snapshot in several years and look at the proper motion of all the detected sources and to see whether they move the same way with the central source. But here you have companions at 20,000 AU, so we would need to wait decades before we can see maybe half a milliarcsecond change in the position, which is not doable now, or we can do, but in 20 years or so. So for now, we rely on the statistical means, and we compute what we call the spurious associations, which is the likelihood for the detected sources to be bound to the central star. And how we do that? So we use galactic models to estimate what is the background stellar density and the foreground stellar density. And then for each of the detected sources, we compute the probability for these sources to be found around this star. And we have a good expertise here in Leuven because there was Alan, Madalena, and Tine. They are really good at doing this. So it was quite easy to transpose the way they use it for sphere to transpose it for the NACO instrument. So once we have the physical parameters, we can get from the pixel positions the angular separation and the physical separation if we use the physical distance to the star. And then from the flux from the feed flux, we can get the flux ratio and also magnitude difference in the L band. And all the sources that had a spurious probability greater than 20% were discarded. Yeah, I think only 2 of them were discarded in the end. So we derived the following parameters. We found that only 8 systems out of 13 were in multiple systems. So it leads to a multiplicity fraction of 62% and a companion fraction of 2.4 on average. So here I plot for each system the distribution of the companions. You see like their projected separation, and the size of the dots gives you the magnitude difference with the central star. And this again is very important to try to understand what is the formation history of these companions. So for companions with separations greater than 10,000 AU, we know that disk fragmentation is less likely because we haven't spot any disk accretion around massive star that is that big. So it's most likely core fragmentation or capture, or other different dynamical interactions such as outward migration, if we still think that these companions have formed through disk fragmentation, to be found that these large separations, they were probably ejected from the system. Also, yeah, there can be interactions between multiple systems and partner exchange or shifting hierarchies in gas-rich environments that will then reshape a bit the structure of the different systems. For the companions that are found within 5,000 AU, disk fragmentation is still the most likely channel. Yes, as I just said, massive stars can have disks up to a few thousands of AU, and it has been shown recently through simulation that the more massive the disk is, then you are more prone to fragmentation as well. And these companions, of course, can migrate to spectroscopic orbits, but this migration depends on so many different factors that we just cannot probe with this type of observations. But yes, there are so many things that are at play also to have a successful migration inward. And then there is this range of companions here that there is kind of like a gap in the formation theories that we do not really know what's happening. So this companion can be captured companions that are maybe migrating inward. There also can be close companions that are experiencing some outward migration as well. That is also possible, like in the disk. If you have some encounters with other companions, then they can be ejected. And also, yes, it can be also the result of a hierarchical star formation, such as triggered star formation. So this is a theory that has been recently proposed. So basically, you form star and companions, but due to the outflows, for sometimes if they are powerful enough, they can trigger again a star formation in the remaining material that is around the star. So yeah, this is also a possibility. So the takeaways for this project, we found a lower multiplicity fraction, but they are at the MYSO stage. So yeah, the structure is not completely set. Yeah, core fragmentation and capture appear to be the most likely channels, but also we know that dynamical interactions are yet to be happening in these regions. And I think the final plot I would like to show you is this one. So this only focuses on massive stars, and we show the evolution of the multiplicity fraction as a function of the evolution of the star. Yeah. And for future work, so I put this chart again. So we have worked with long baseline interferometry, with adaptive optics imaging, and I know that Madalena and Tine are doing great work in bridging the gap between adaptive optics and long baseline interferometry using sphere and high contrast imaging. What we would like to do also, and what I'm doing right now as a third project, is to explore a bit more these quasi lead-off effects in highly eccentric triples. So again, I use long baseline interferometry because we know that For causal lead-off effects to happen, usually it's a central spectroscopic binary surrounded by a third star, and this third star is detectable by interferometry. So I try to constrain their orbits because we have snapshots for more than 10 years, so we have enough points to actually build the orbit. And Laurent Mailly, former postdoc at IvS, works on the spectroscopic side. So we are going to put our results together and try to understand how these causal lead-off effects can happen. And last, again with interferometry, I have an accepted proposal with gravity again to look at M17, but now at the MYZO stars. So they were initially in the first proposal, but they had some issues with gravity and they couldn't observe them. So we also have this ongoing proposal, and it would be great to see if the results in M17 extend to the MYZO phase as well. Yeah, thank you.
Thank you, Emma, for a very nice talk. I personally now understand much more about how interferometry works. And looking at all the challenges you guys have in the data manipulation, I think we spectroscopists should stop, I think, talking about issues with our spectrum normalization or, you know, fitting a second degree polynomial to a light curve to correct for systematic sort of stuff. Also, congratulations on 2 papers, first order papers, and also on the fact that I think your seminar is the very first IvS seminar attended by the department head. That's something. Questions in the audience? I'm sure there will be many. Ah, yeah, the department head. Okay, go ahead.
Thanks for your talk. I have a question about the flux ratios in your binary in the first system, because it's a wide range from 3% to 80%.
Yeah.
And I wonder, the 3%, is that really, I mean, that's not a lot. And there is still, so that's one question. So how sensitive, or what is the detection limit, let's say, of that flux ratio? And the other one is, you do not include dust. So you do not include unresolved components in your model. Is that not a limitation because it's still quite embedded?
Yeah, good questions. So for gravity, finding 0.03 is not that strange because you can go down to a magnitude difference of 4, which is much more sensitive. So you can go even deeper. And then for the second question, so as I said before, we know that they have reached the zero-edge main sequence, and indeed, with gravity data, we also got medium resolution spectra, and we do not find any signature of disk, for example, with the bracket gamma line. So we did not include dust in the models. We tried for some of them where we had some residuals, some signal in the residuals, and actually for one of the systems I haven't shown it here because it's a really complicated system. But we found that it's actually a triple and that the outer companion is surrounded by an asymmetric disk. So we also question here if there is like a hierarchical star formation processes happening or something.
More questions? I'll start from here.
Yeah, thank you. Great presentation. I have maybe a very naive question. You make a difference between disk fragmentation and core fragmentation for the origin of these binary systems. In practice, what would be the consequence, I guess, on what we expect to find in the system, or dynamically what happens?
Okay, so the main difference is basically the separation at which you will find these systems, because core fragmentation, like the scales are really big compared to disk fragmentation. So I think this is more something that is traced by ALMA, for example. They have evidence, for example, of core fragmentation. I think it's a paper that was released this year or last year. They have this really nice picture with also the gas flowing and the kinematics, so they know that it's really like this system is formed through core fragmentation. But it's really a matter of scales that you are probing, basically.
You don't know of particular I don't know, features that we would expect in one case compared to the other. It's just like more a matter of, yeah, at these scales that we don't find disks, so actually
Yes,
it's cool.
most likely, but I think then some features that I'm thinking of, I'm not sure if dust-wise you can find stuff, but probably in the dynamics of the gas and the infalling material itself. So yes, looking at maybe also wider scales and with the cold dust, so ALMA, submillimetric or radio, and try to maybe understand more the kinematics of the surrounding and infalling gas. Will probably give you hints. Yeah.
Okay, thank you.
Thank you, Emma, for this nice seminar. I have a small question to one of the plots you showed in your first project. I think it was like the delta magnitude against separation, if I'm not mistaken. Yeah, that one.
Yeah.
I see some like kind of edges to this plot. Is that physical edges, or is it like observational biases? For example, there's nothing in the lower
blank here.
Yeah, the blanks, the blanks.
Yes.
Pages,
So this blank. What you have to know also is that the blue dots are taken with Pioneer, which is in H band. So this is the best angular separation you can get with the VLTI at the moment. For why we have this blank here is due to probably the sensitivity of gravity that has now been updated and upgraded with gravity feint. So now you should be able to fill this area. So it's it's a bias. It's not optional, but yeah.
Thank you.
Thank you, Emma. That was a very clear presentation. Also on the first project, I had a question because I don't really get why you need to have the phase curve for your companions, because the visibility curve can already give you the presence and separation of your companions. So why do you need the phase curve?
Yeah, so the phase curve, we use it like first because we have them, we have to use them, and also to trace the asymmetries because it really helps in constraining the flux ratio of your binary systems. So for example, you have you can have degeneracies in the visibility models when you fit them, but then when you add the closure phase component, then it really helps in restricting the different models that you can have. So yeah, that's why we use them.
Okay, thank you.
All right. Well, I'm walking to Pablo and then back to Ake. Would be nice to see more hands.
Hey, thanks. That was really nice. I wanted to ask a bit, I guess it connects to this plot where you put 3 binaries, 3 triples. You were mentioning that you fit things until you're done fitting. So I'm curious, what does that mean? Because a more complex model will always give a better fit.
Yeah, good question. When we reach like chi-square of 1 point something, sometimes between 2 models you cannot really say like you have maybe a 0.1 or 0.2 difference in the reduced chi-square that you derive. So in order to choose between 2 models, we perform the F-test, which is like a statistical test to discard between 2 different chi-squares. And also we preferred to go to like lower order multiple systems than trying to like add up, and then we don't know really know what to do with that. So yes, but this was this problem happened for 2 systems actually, where we could fit with almost the same chi-square binaries and triples. So we discussed also the capabilities of gravity, how deep we can go. And this statistical test was the final test to differentiate.
Okay, and one other quick thing. You were mentioning that for these systems, you had a few of them that were identified as spectroscopic binaries.
Yes.
So are these, when you say 3 binaries?
This is only interferometric.
So that's essentially that there's a binary and you are detecting a triple?
Yes, indeed.
Okay.
Yes.
Thanks.
Thank you, Emma. I also have a question on the interferometry. So yeah, what about Shara? So longer baselines, can we use them? Are people using them for MYSOs or
Yeah,
like these systems
Yeah,
with the
good question.
binary separations?
Yeah, that's a great question as well. Yes, there is a team of Leeds and Exeter in the UK. They use a lot Shara for MYSOs as well. It's true that with Shara you can probe even like closer or best angular resolution because you have longer baselines and you can go almost in the optics, I think, with Shara. But yeah, it's something we can do. It's just that these data sets are only observable in the southern hemisphere, so that's why we went for the VLTI. But of course, this can be done also with Shara.
Okay, thank you.
More questions? If not, maybe a couple from myself. So Emma, you showed us multiplicity fractions that you obtained. Are those the observed ones or bias corrected? And if the former, how can you correct for the biases?
Which ones you mean?
In the first and the second project, so you report 100% and 62% multiplicity fraction. Is that bias corrected or not?
So for interferometry, this is something that is debated within the interferometry community, whether you have chance alignments and all that applying also in the interferometry. I personally think it's not the case because you really need two close-ish systems for the fringes to, or for the beams to interact, to interfere, sorry. They were not finally bias corrected. For the NACO images, neither. We are at the moment also discussing with the referee whether or not we should have more statistics involved in this result. Yeah, none of them are bias corrected for the moment.
Thank you. And maybe second question. So with those high percentages multiplicity-wise, what could you tell to the folks in this audience who still compute their MESA models for 8+ solar mass stars in a single star scenario? Is there a message you want to convey?
That you should maybe add a second star. Yeah. I don't know what to tell you exactly, but I think it's good to know also the evolution from a single star because we know that they exist, the single massive stars, once they have swept everything that they have around them. So, yeah, it can be.
Okay, thank you. Your last chance to ask a question. Yes, Luke.
Yeah, maybe just a quick question. So, yeah, great talk and very nice results. You talked a bit about adaptive optics at the VLT. Are you excited about ELT?
Yes, of course. Yeah, I think the adaptive optics will be much better because it's already integrated in the construction itself. So, yeah, we'll see with Metis what we can do.
All right. Let's thank Emma again for a wonderful seminar. And before you leave for lunch, quick reminder for the seminar announcements, please check newsletter, okay? And go to Advalva's pages as well, because there is a lot more information on those pages than in a PDF announcement. That looks nice, thanks to Nadia for the design, but you'll find more information on the seminar pages. Thank you, see you next time, next week.